In this video, we'll be taking a look at a number of common prescriptive process models. These are process models that advocate for a very orderly and rigid approach to software engineering. But first, what is a process model? Well, you may recall from our previous video where we discussed the software process framework that a software process is a collection of activities, actions, and tasks that define what needs to be done to complete a software development project. When we combine a process with a process flow, which describes what order we complete activities in and how they flow between them, we get a process model. In our previous video, we talked a little bit about tailoring your process for your specific project. However, it's not always necessary to create the process model you'll be using completely from scratch. There's many existing process models that can be adapted and customized for your needs instead. So the category of process models we're going to be discussing in this video will be prescriptive process models. And we call these prescriptive as they prescribe a set process flow. These are models that strive for structure and order, but this comes at a cost. And this is a cost at handling change well. We discussed previously how change can be one of the biggest risks for a software project. So these models also require extensive documentation and design work. And it also recommends that activities occur in a specified sequential order or have some rigid guidelines for progress. So these prescriptive models also tend to work well for well-understood problems and smaller projects. They can also be an ideal starting place for less experienced developers and development teams, which is why we're going to be starting with this video describing prescriptive models before we move into agile models in a future video. The first model we're going to be taking a look at is the waterfall model. And the waterfall model is a very sequential approach to development. And this tends to work well when we have very well understood requirements that are well defined and they're unlikely to change. It can also work well when we're doing enhancements or modifications to an existing system. In this waterfall model, activities happen sequentially, each flowing downward to the next. So communication leads into planning, which leads into modeling, and so on until deployment. This downward-only flow is the reason that we name this waterfall or the waterfall model. It's one of the simplest and oldest models in software engineering, but does have a few problems. So the main issue is that there's no iteration or any way to return to our previous activity. For example, if during the modeling activity, we find that we understood a requirement incorrectly or the stakeholder suddenly requests an unexpected change, there's no easy way to return to a previous activity. Work would need to stop, requirements renegotiated, and some amount of planning redone before we could start again. This leads to the model not accommodating change well and failing to include stakeholders throughout the development process, which is a big issue. Another issue is that testing only occurs during the construction activity, which is rather late in the process. This means errors introduced during requirements modeling and design work aren't going to be caught until late in development. Similarly, feedback is not sought from stakeholders until the end of the process, making correcting defects or any changes requested by stakeholders very costly. There are a few positives, however. It's fairly easy to understand model, and it's well understood, making it very suitable for beginners, and most steps are straightforward, making it simple, making it easy to understand, and making it suitable for small projects without adding too much overhead. There's not going to be much documentation added here or any complex steps. So the next model we can look at is the V model. And this is a variation of the waterfall model, which attempts to add quality assurance steps and testing to each activity. The traditional activities are on the downward arrow, but after code is gathered, the team moves up the right side of the V, carrying out tests that validate the work done to date in those past activities. So the idea here is that our key framework activities are happening going down the left side of the V. Those would be things like requirements gathering, that'd be communication, our architectural and component design, that would be modeling, and code generation would be construction. Then when we're going up the right-hand side of the V, we are doing tests and validation to confirm that we did things correctly. So unit testing would help confirm that what we created during creation or code generation actually works. Integration and system testing would be testing our design, and acceptance testing would be validating that the requirements we gathered are actually fulfilled and accepted by the stakeholders. This does have a few advantages over that waterfall model that we just saw. It remains fairly easy to understand, but it adds additional testing steps. Being based on that waterfall model, it also continues to be suitable for small projects as well as novice developers. But being so similar to the waterfall model also raises an issue. And that is the most significant disadvantage here. And that is that it's effectively the same as the waterfall method. There isn't any real differences here. All of these steps down on the right of the V, as well as code generation, are simply the construction activity. Remember when we talked about those key activities, construction does include testing. The waterfall model here, is being effectively split and folded to create a V shape, with some activities being split up. This means that it's going to have the same negatives as the waterfall model. It does not accommodate change well, testing still occurs too far late in the process, and customer approval isn't sought until the end of the process, meaning that we're still not including stakeholders through the whole process. So while we might get a small advantage in that testing's more well-defined and more encouraged, it basically is the waterfall model. So the next model we're going to look at, which hopefully offers an improvement, is the prototyping process model, which offers a number of advantages over the waterfall and V models. The prototyping model begins with communication and requirements gathering. Once requirements are gathered, a plan is created for the development of a prototype that's going to include just the key features. Quick models and design work are then completed, which focus on aspects of the software visible only to the end user. This design is then used to construct a prototype, which is then deployed to stakeholders and their feedback is collected. This feedback is then used to start the process over and create a new, more refined prototype. This cycle continues until the prototype satisfies all of our stakeholders' requirements. The big advantage here is that the prototype serves as a way of identifying and validating requirements from stakeholders. Stakeholders get a feel for the actual system and are included throughout development, and developers get to build something immediately, which most programmers love to do. This leads to reduced likelihood of the project being rejected, and any issues raised by the stakeholders can be addressed during the next iteration. This tends to work well for small projects or projects that have user-facing parts that can be rapidly prototyped. For a larger project, it can also be incorporated into another process. For example, you might use the prototyping process to develop just the user interface, but you might make use of another process for the overall project. There are downsides, however. No process is perfect. So for the prototyping model, this level of customer involvement can lead to delays. Waiting on customers to provide feedback can mean that you are stuck doing nothing until they respond. There's also often a temptation to ship a prototype before it's ready. Customer might see what appears to be a working prototype as the focus is only on the user-facing features, when many important back-end aspects are still in development. As a developer, there's also a temptation to take shortcuts to get a prototype working quickly to meet your deadlines. This can be fine for a prototype, but if you're not careful, these shortcuts and temporary compromises can become a permanent part of the system, which leads to reduced quality. There's also a chance of work being lost if a prototype needs to be thrown away based on feedback or a change in requirements, which can make the process harder to plan for and can be a bit frustrating for developers, feeling like their work was for nothing. The next process we're going to be taking a look at is the spiral model. And this is a type of evolutionary process model. These evolutionary models are designed to solve the problem of producing software rapidly. In real life, we often face business pressures or competitive pressures to get software out before arrival, or to be the first to enter a new market, or maybe to meet some deadline. And this requires being able to make software very fast, even if it's not fully perfect at first, and then sort of evolve it or make it more developed over time. So the idea here is that a more refined or evolved versions of the software are created after the initial deployment, and then we add more additional features, correct defects, and create more complex systems over time. But we get out of the gate right away. The spiral process model in particular combines the iterative nature of prototyping with the more controlled and systematic aspects of the waterfall model that we saw earlier. This process starts in the center of the spiral that we can see on the screen right now with the communication activity. The other activities are then completed in a clockwise direction, spiraling out from the center, going through planning, then modeling, then construction, and then finally deployment. Each completion of this spiral results in a progressively more sophisticated version of the software, and feedback from stakeholders and users is used to guide the next iteration, or the next spiral. At each planning phase, the project is reassessed, and the cost and schedule are adjusted as needed. One of the key features of this spiral process is the risk-driven approach. As the software is created in small increments, risk can be assessed continuously, and the project plan can be adjusted as needed. As we just saw, we adjust the project plan each time we complete a spiral, or an iteration of the software, based on feedback from our stakeholders, as well as how the last iteration went. So unlike other models, where the final goal is just delivery of the completed software, in the spiral model, these iterations can continue even after the project is delivered to support maintenance and the creation of future versions of the software, meaning we can use the same process for both development and maintenance. Another advantage of this approach is the continuous customer involvement and risk management. This makes it ideal for large and complex projects, as well as projects that will need extensive support for future versions. It also works well when there is an immediate need to create and deliver software and expand it into a more complex system in the future. But there are some downsides. The spiral model requires some experience in project management and risk analysis to use successfully. If any major risks are missed or not managed properly, significant problems will occur and derail the project. That means we need an expert team of developers to properly balance flexibility, extensibility, and speed of development and ensure customer acceptance. So that brings us to our last process model. And the last one we're going to take a look at is the unified process model. The unified process is another evolutionary model, but unlike the others we've seen so far, it attempts to incorporate aspects of more agile models. Agile models are something that we'll be discussing in our next video, but for now, this means more customer involvement, lighter documentation, and streamlining methods for capturing stakeholder requirements. The unified process is also created to closely align with the use of use cases and the unified modeling language. Both items we're going to be getting far more into later in the course. Unlike the processes we've seen so far, which have a fairly distinct separation of the key framework activities, the unified process has 5 overlapping phases that encompass these key activities. The first is inception, which includes customer communication and planning. This phase aims to capture requirements as use cases, identifies resources required, assesses risks, and sets a schedule for the first increment of the software. The inception phase overlaps the elaboration phase, which includes both planning and modeling activities. The use cases that were captured in inception are elaborated on and refined, and modeling is done to design the architecture and components of the system. Construction remains the same as in other processes. Code is generated, and each use case is implemented. As components are created, they're tested individually and integrated into a whole. In the transition phase, the constructed software is delivered to the customer and feedback is collected. This phase includes both the later aspects of construction, including creating necessary support documents, such as user manuals, installation guides, and so on, and early deployment actions, including delivery of the software and stakeholder evaluation. The last phase is production. During production, ongoing use of the software is monitored and support is provided. Bug reports and change requests are submitted, and this feedback is used when we're creating future increments of the software. Now, one thing that should be noted is that these phases can occur in parallel, and that's not really shown in this diagram. For example, the production phase may be ongoing after a release, while inception or elaboration are underway on the next increment. The advantages of this process model are its focus on quality use cases and UML-based documentation, as well as its continuous inclusion of customers and their involvement in the process. The evolutionary approach that we're taking here to development makes accommodating changing requirements possible, and it lends itself well to ongoing maintenance projects, as well as new developments. The disadvantages largely come from the complexity of the process and the overlapping phases. This requires an expert development team and project management that have experience in this process, as well as use cases and UML. So these prescriptive process models that we've reviewed so far are some of the most common, but there are many more out there, and teams may also come up with their own or tailor them to their specific needs. What is shared among them is that they all tend to be highly structured, they tend to be very rigorous and rigid, and they don't tend to handle change well, at least as alternatives like agile models that we'll be talking more about later. That being said, they are still appropriate for well understood or small projects, and they do make an ideal starting place for less experienced development teams. In future videos, we will explore those agile models that I mentioned, which offer a less rigid and more flexible approach to development that have become quite popular in the industry. But for now, that's all I have for you on process models. So until next time, thank you for watching and have a great day.